Good morning, everyone. I'd like to start by thanking Christine and the organizing committee for putting this fantastic workshop and looking forward to the rest of the talks today. So let me start by reading the statement up. The QuDits space is ideally suited for performing molecular simulation for both structure and dynamics. So my research dealing with molecular systems, and if you look at the potential energy surface here, you have electronic states, vibration states, rotational states, and you add the spin, and you can see clearly you have multi-level quantum systems, and QuDit is the platform to do these kind of simulations. And since we have this workshop in QuDit, allow me to also present this review article that we did with Barry. And this is about QuDits and high-dimensional quantum computing. We start with introduction to the field and went to the gates in QuDit space, algorithms, and then implementation. So in my research group, as I mentioned, we are dealing with molecular systems. So we're developing quantum algorithms and implementation, quantum devices for electronic structure, open dynamics. If this molecular system interacts with environment, how do you simulate the quantum master equation on a quantum computer? And then also we're dealing with quantum phase transitions, and how do you perform finite size scaling on a quantum computer, because no one can do calculation with infinite space. So we have also a systematic way to do finite size scaling on a quantum computer. And also doing a quantum machine learning. But today I'm going to focus on our recent work on simulating chemical reactions, and mainly how do you calculate the cross-section or the probability distribution going from the reactant to the product. So here's the outline of the talk. First, I will explain how interference is an important phenomenon in quantum reactions. And then I will talk about the simple algorithms, how to go from reactant to the product and calculate the cross-section. And then I will show results for the simplest chemical reaction, which is the hydrogen atom. In atomic physics, we scatter hydrogen with H2, and we go from vibration V to V prime. And then I will talk about conclusion and future work. So now when we deal with quantum information quantum computing, we are talking about superposition, which leads to qubits and qudits, interference, which is the heart of quantum algorithms, like in the celebrated algorithms by Shor, where you design your algorithm to take advantage of the constructive interference to calculate the period of a function, which allow you to factor a number. So interference really is the heart of quantum algorithms, and entanglement, which is a strong quantum correlation without a classical analog. And just to give you the overall, we're trying to see how these effects can be included when you go from reactant to product. And can you control outcome of chemical reaction using superposition, interference, and entanglement? So when we talk about interference and we teach quantum mechanics, we go to the two-slit experiment. And why is it so important when you talk about particles going through two slits? This was already demonstrated experimentally with photons, electrons, neutron atoms, and even large molecules as C60. And if you look at the probability distribution for 1 and 2, and then you allow for superposition, and suppose we are talking about two different mechanisms in the chemical reaction, and one with the amplitude 10 times bigger than the other amplitude. So if you look at the P1 and P2, and you see the difference, the variance is only plus minus 1%. But if we take a plus and minus and then you square it, you see the effect is 20%, which means small mixing here between the two channels lead to a big effect. And we're going to see this big effect in chemical reactions when you think about the interference between two pathways. So if you look at the double-slit experiment with Feynman lecture, this is what he wrote in these lectures. He said about the double-slit experiment has in it the heart of quantum mechanics. In reality, it contains the only mystery the basic peculiarities of all quantum mechanics. And as I mentioned, quantum interference is really the heart of quantum algorithms. So we'd like to connect the two in the field of chemical reactions. So this is really the goal here. So the first experiment I would like to mention where interference was important, and this is taken from the article by Dick Zare at Stanford and his group, and they published it in Nature Chemistry back in 2015. And they talk about the scattering between hydrogen and deuterium D2, and they look at the cross-section of the scattering, and they see oscillations in the results that cannot be explained with the classical trajectories. And just to summarize the main conclusion of this paper, they said interferences are genuine quantum phenomena that appear whenever two seemingly distinct classical trajectories lead to the same outcome. So just to be more precise about the experiment, they look at this reaction with D2, go from V0, J, 0 or 1, into the product HD with different V and J, and they look at the differential cross-section as a function of the scattering angle. And you see the experimental results. The solid line is the full quantum calculations, so you see oscillations. The red line here is the classical calculations. And you can see you cannot capture the classical oscillation in the cross-section with running classical trajectories. So they went back to the classical trajectory, and they're trying to analyze what is going on. And for that, they look at the deflection function, which is a function of the total angular momentum and the scattering angle. And you see the different mechanism, classical mechanism. One, for example, this one, and two, 1 and 4. 1 and 4, they scatter at the same, very close to the 130 degrees, but different angular momentum. If you look at the mechanism 3 here, and 2, they scatter around 180 degrees with different angular momentum. So what they did, they went back to the quantum calculations, and they look at the interference within this window of J in the partial wave analysis, and they show clearly that the interference between these different classical mechanisms will lead to the oscillation in the cross-section. So this was the experiment, and this was published in Nature Chemistry. So another experiment where the superposition makes a difference. This is given by Yang Chen at Purdue, and this was Physical Review Letter back in 2018. And he looked at the Bose-Einstein condensation of rubidium atom with the hyperfine F equals 1. And what they did, they look at the photo association. So they scatter the two rubidium atom, and they absorb photon. And once they absorb photon, they go to the excited state and form this excited molecular system. But what was surprising in this kind of experiment, that it depends on the initial superposition of the spin states. You can control the outcome of this chemical reaction. So let me just be a little bit more specific here, just so you can see. So remember, this is hyperfine structure F equals 1. So M sub F, you have 3 states, 0, -1, and +1. And they show in this kind of experiment, you have 2 channels or 2 reaction pathways that lead to the total F equals 0. So you can scatter with 0, 0, or scatter with -1, +1, or +1, -1. So they think about this kind of experiment as 2-slit experiment. And they examine the interference between the 2 pathways. I will not go through the math, but let's look at the rate of the reaction normalized to the one that you don't have superposition. And the C0, C +1, C1 are the coefficient for the wave function. And when you calculate the rate of this reaction, you see this minus sign here, which means there is a destructive interference. There is a destructive interference in this reaction for this particular spin configuration. And then when they look at the experimental results, they look at the rate of this chemical reaction as a function of Raman coupling between the state or as a function of the Raman detuning. And you see the destructive interference. These are the experimental results. Yellow one is the destructive interference. And this is the theory part, no interference. And you can see clearly that this superposition of the initial state lead to destructive interference, and there is no outcome in this process. And later with my graduate student, we asked this question, under which condition with this superposition you see constructive interference? So experimentally they say destructive interference, and the question is, can we see constructive interference for this kind of reaction? Anyway, we worked out the theory for this one, and instead of going F equals 0, you go F equals 2, and you see we changed the sign here in the reaction rate between minus and plus. So now we have a constructive interference between the two pathways, and this one will lead to, yes, you can have a chemical reaction and form rubidium-2 in the excited state. So we did the theoretical calculation, and this is the constructive interference, and you see enhancement in the reaction rate, again, for the Raman here as a function and the detuning. And now the Yong-Chen group is trying to come up with the experimental verification of this theory to see how constructive interference lead to the reaction. So just to summarize, we have seen in this reaction that the specific configuration of the spin state can lead to constructive or destructive interference in the outcome of this reaction. So this was the experiment with Yong-Chen, and now we're looking back. I mean, I'll come back to the end of this. Like, if instead of looking at the hyperfine state here, I mean, also the Dixer group and others, they can control also the rotational states. So we are examining theoretically if we can repeat this calculation where you take into account the specific configuration related to the rotational states and see if you can control the outcome of these reactions. So again, we also asking the question, does entanglement play any role? Because this is only superposition, and so far we don't see any role for entanglement. But for that to connect with the scattering states, we just have to generalize Bell inequality to entanglement where you scatter, so you have to go from discrete to continuous inequality. So we can see when you scatter these states, so with 4 mechanism, can we see if you violate the Bell inequality? So just to summarize what we are talking about here, we are trying to see how the superposition of the initial reactant can control the outcome, and we see this in the spin state with the wrong Shin experiment. And we ask, can other degrees of freedom, like vibrational, rotational states, can also affect the outcome of chemical reaction? And we are still working on entanglement because we haven't seen yet if there's any role for entanglement in the reactant which affect the product. So we said, okay, now can we run this experiment on a quantum computer? Because in a quantum computer it will be easy to manipulate the initial superposition of the state. So the goal now said, okay, can we run this experiment on a quantum computer and see the effect of interference or superposition in the initial states? So this is what I'm going to focus now. How do you do this scattering on a quantum computer? So to do this, we start with the simplest reaction, H plus H2. This is the simplest reaction, and we see how one can run it on a quantum computer, and we look at its colinear collision. And this slide will summarize what I'm going to do next. So to do the scattering, first you have to come up with potential energy surface for the H3 system. And this is an old topic of research in chemistry. I mean, people developed this potential energy 40 years ago. And there is one accurate potential energy surface describing H plus H2. And I will go through more details once we start doing the implementation on a quantum device. So you need potential energy surface and then your reaction coordinate to describe the scattering. So for example, I mean, you can see this is the relative coordinate, and this is the internal one for the reactant, and this is for the product. But once you reach the scattering or the transition state, we go with what we call the bond coordinate X and Y. And the goal of the experiment is to come up with the probability distribution or probability for the reaction from the reactant from H to H2, and with changing V to V prime. So this is what they got with the full quantum calculation, and we'd like to see if we can repeat this one on a quantum computer. So let me just explain the main idea. I will go through more detail. We're going to use what people have done. This is back 1993 with full quantum calculations using the Møller operator formalism for scattering. And the main idea is very simple. You prepare this is state to state. So at the end, you would like to calculate the scattering matrix element between alpha and beta. Alpha for the reactant, beta for the product. And once you calculate the scattering matrix element, the probability distribution is the absolute value square. And the way you get the matrix element for the scattering matrix element, first you calculate the correlation function between the two wave buckets. So what we're going to do, we're going to prepare two wave buckets, one for the reactant and one for the product, the state to state. And then we'll move forward in time with the reactant to the transition state, backward in time for the product to the reaction center here, which is the transition state, and then calculate the correlation function between the two wave buckets. So this is the formalism done 40 years ago in quantum calculations, and we thought this is the simplest one to follow up on a quantum computer. So again, wave bucket in the reactant, wave bucket in the product, forward in time, backward in time, calculate the correlation function for both. And from the correlation function, when you take the Fourier transform, you get the scattering matrix element. So this is the formalism and used for 40 years. And we followed this paper by Weeks and Tanner from 93. So potential energy surface, there's very accurate potential for H3. And this is developed back in 78. And people kept refining this to get more and more accurate by just ab initio calculations. This is simple calculation. You have H3. And this can be done accurately with ab initio calculations. So when we talk about the quantum algorithm, there are 3 steps. And preparing the wave bucket for the reactant and the product. So I mean, you can also prepare this one in quantum, but we just, for the sake of running the algorithm, we focus only the quantum algorithm on the correlation function. So we calculate the correlation function on a quantum device. And we do the Fourier transform classically once we get the correlation function. So this is a classical step, preparing the wave buckets. This is a classical step, calculating the Fourier transform. So the quantum algorithm, we calculate the correlation between the two wave buckets in the reaction, in the scattering regime. How much time? 10 minutes. So again, we'll go through the Møller scattering approach. So first of all, you prepare the reactant wave bucket with the asymptotic Hamiltonian. So asymptotic Hamiltonian have 2 terms. One is the relative motion for H to H2, and the one for the vibration of H2. So it's easy. This is the asymptotic Hamiltonian. And the small r for the internal coordinate, big R here for the relative motion. And then we can get the eigenfunction of this Hamiltonian in terms of the R here and the capital R. And you can move it to momentum space where gamma here and K of gamma. And we do the same thing, the asymptotic wave bucket for the product. And again, with the asymptotic Hamiltonian, again, you have relative motion with H plus H2. Now, once you propagate forward in time, backward in time to the reaction center, you work with the full Hamiltonian. So this is the asymptotic Hamiltonian plus the potential energy that describe the H plus H2 scattering, the H3 potential energy surface. Now, with this formalism, you have to define the Møller operators, and you can see clearly the plus sign go with the product, with the reactant, and forward in time. For the minus sign is the reactant, the product, and you forward backward in time. So you see backward, forward in time. These are the operators for the asymptotic one plus the full Hamiltonian, and then you define 2 Møller states. And the 2 Møller states are the 2 states that already forward, backward in time to the reaction center. And again, as I mentioned, the main thing here to calculate the correlation function between the two Møller states with the full Hamiltonian, take this correlation function and do the Fourier transform, and you get the scattering matrix element. And from this, the absolute value square is the probability distribution or probability for the reaction to go from the reactant to the product. Now, for calculating the correlation function is very simple. I mean, this is a trivial algorithm. This is what we call the Hadamard test. And the Hadamard test is a simple algorithm to calculate the expectation value of U unitary between psi and psi. So you have two terms, the real part and the imaginary part. So calculating this one, you prepare the state here, and you need control H, control U here, and this is the Hadamard. This gives you the real part. And if you insert here the phase shift, which will give you minus I in front of the 1 when you do the Hadamard, and you control, this will give you the imaginary. So, I mean, Hadamard test is a simple test that we use to calculate correlation function, expectation value of this operator. I mean, for us, we have to modify this one, because remember, we have two wave buckets coming from forward in time, backward in time. So we have to modify it. And there is a modify test if you have access to two unitaries, U1 and U2. You can modify this algorithm and look at the expectation value of U1 U2 between those two states. And for us, U1 and U2, one will be the Møller operator forward in time. U2 will be Møller operator backward in time. So we can modify the Hadamard test on a quantum device and see the correlation function. So I will not run, it's a very simple algorithm. I will not run, I mean, it's a very trivial algorithm. So let's just go to the state. So as I mentioned, you have the Ancela qubit here, which will encode the results. So you have Hadamard, the shift here, and then this is U1 and this U2. And these are representing the Møller states. So phi1, this is the Møller operator for the product, and this is the Møller operator for the reactant. So now you have to break down all these propagation in time to get U1, and this is propagation in time for U2, which allow you to go forward, backward, and calculate the correlation function. So as I mentioned, we have 3 steps, and we run this tau from minus tau to tau, and my graduate student run it from, I mean, the way we follow the quantum calculations that done 40 years ago, and they run from 40 atomic units to 40 atomic units, 400 to 400, and then you can calculate the correlation function by this modified Hadamard test. So again, if we go back to the colinear, I mean, you can see clearly what is the asymptotic Hamiltonian. So you have the relative motion with capital R and the vibration for H2. And once you reach, so the reactant R1, R2, the product will go with the R2, R2, small one here. And once we reach the transition state, we move to the coordinate system, what we call the bond coordinate X and Y. So it's easy to work with this one in the transition state. So this is the full Hamiltonian that we're going to work with, the momentum in X and XY here. And then this is the potential energy that we took from this LSTH. These are the names of the author that developed this potential energy surface for H3. So these are the wave buckets here. And so again, these calculations are, I mean, was most of the PhD thesis for my student. I mean, there is a lot of calculation involved numerically here because you have to write the Hamiltonian as a sum of Pauli matrices. And what he did, he took just to initialize this and see the results, we took 10 qubits. And this is first quantization, discretizing the space, and encoding the system in binary. And then run the calculation and see the correlation function. Anyway, I will mention that at the end the reference. We have the appendices with all the details and the quantum circuit and exactly all the details if you need to rerun it on a quantum device. So what we end up with this calculation, we calculate the correlation function as a function of time. And what we describe here, classical, is the full quantum calculations, and a quantum is the quantum simulation. And you can see there is a full match between the two calculations that in a quantum device, I mean, this is simulation, and this is full quantum calculations for both going from 0V to 0 or from 0 to 1. This one, 0 to 1. So there is a match between the simulator results for this reaction and what we have used from this paper back in '94 for H plus H2, which means in principle one can simulate this reaction on a quantum device. So once we have the correlation function, we can do the Fourier transform as a function of energy and get this the probability distribution or probability for the reaction from 0 to 0. And this is the probability from 0 to 1. And you can see there is a full match between the two calculations.
Classical here is
classical. Classical means full quantum calculation, sorry. Okay. Yeah, it's confusing because you say classical computer. Yeah, so we see, sorry, we say classical, but this is full quantum calculations. But what I say quantum is quantum simulations. So it's just like try to finish by saying, okay, well, about the source of errors, we have two. One is the sampling error, because we're doing this, the modified Hadamard test. And this is known that scales like log 1 over delta, where delta is the success probability here, and epsilon is the accuracy. And the other measure source of error, of course, the propagation of exponential e to the ht, and we went to second order in Trotter approximation. So these are the approximations that we did in these calculations. And so, of course, I mean, you can go beyond second order, but with this calculation went all to the second order. So again, all the results that I mentioned, we publish it in the journal Physical Chemistry Letters, and we have appendices for all the mathematical details and the potential energy surface and the quantum circuit that we did for this reaction. So just to summarize, we started saying we would like to see what is the effect of superposition, interference, and entanglement on the product of chemical reaction. We have seen experimental results for the initial superposition of spin state or spin control outcome of chemical reaction. And we'd like to see how one can generalize this from spin to different quantum numbers like rotational, vibrational states for molecular system. And we show how one can run simple calculations and get the cross-section for H plus H2 in a quantum device, and mainly the quantum algorithms calculating the correlation function between the wave packets, the two asymptotic wave packets. And this is done by the modified Hadamard test, which is known algorithm. Really, the difficulty is just implementation because the potential energy surface is a very complex one. And now the question is, how do we generalize it to more complex chemical reactions? And I thought maybe I end up with this slide for the discussion. And again, as I mentioned, we can also discuss if the superposition, interference, and entanglement can have any effect on the product. How do we generalize it from single state to state to distribution in different V and J? And for that, you need a QuDits space. And yesterday, we have seen the discussion of how to decompose a general unitary matrix. And we discussed how to decompose it into sequence of quantum gate. But what simple approach that we did back in 2011, we said, OK, can we do this one as an optimization problem? I start with gates from a universal gate set, like rotational C naught gate, C control Z, and work as an optimizing problem. What will be the best optimization, the best sequence of gates that give us this unitary matrix? You can use it as optimization, and was very, very useful in simulating molecular systems, where we know the it's very difficult to decompose the full Hamiltonian. But now the question is, can we replace this one with the for example, QuDits gates and do the same optimization and get the gates needed to simulate it? And the other direction is, I talked about the modified Hadamard test for qubit, but you can also think about generalizing it to qutrit, and I think someone mentioned this for qutrit yesterday, but we can generalize it to qudit space. And again, at the end, the challenge you have to discuss when you go from qubit to qubit, from qubit to qudit, you have to discuss the advantage and challenges. And for that, I mean, you have to discuss if the technology, I mean, how do you implement these can control the algorithm compatibility, scalability, and error rates. So I would like to end by thanking my group. And mainly this was the PhD thesis of Summit that I talked at the end, but some of them are involved in other aspects of the research and funding, and thank you for your attention.